Good evening, children. Good evening, online children.
Good evening, ma'am.
Good evening. I've shared my screen visible to all of you.
Yes, ma'am.
Okay. So recalling about circles, we had already finished in exercise 9.2 in circles. Volumes and surface areas, we finished the first three exercises. So I have the fourth one to complete, but I just want to revise, give you a test based on the first three exercises. So that mostly we'll take it tomorrow. So I'm not continuing with the fourth exercise. So tomorrow you'll be taking a test on volumes and surface areas based on exercises 11.1, 2, and 3, the first three exercises out of 4. All right, so I thought I'll do circles today. Test meaning practice test kind of, like not the test where you are left to do it on your own. So you will try, and I'll also, if you're not able to get the answer, we'll see the answer immediately so that at the end of the class, like you've learned something. Okay. Join Blessing, join Jayvarshini in the class then. Do whatever she's doing. So this is circles, exercise 9.3. So quite likely that, we might have forgotten the theorems of this chapter. It's okay, we'll recall. So like when we do the sum, whatever theorems or theorem has to be recalled, we'll do it and then go to the next one. So like that. So in this figure, AB is a diameter. So when it is diameter in a circle, we know that there is a theorem related to this. Angle in a semicircle is a right angle. In a circle, when you know any of its diameter, okay, so here in the circle with center O, AB is the diameter, all right. So now based on this, we have a theorem from this chapter. Angle in a semicircle is a right angle. I just started, Giant, you haven't missed anything. Angle in a semicircle is a right angle, which means take any point on the circumference. Okay, so say C. Join the ends of the diameter to C. Join the ends of the diameter to C. Ends of the diameter. A and B are the ends of the diameter. Okay, so join that to C. This is 90 degrees. Angle in a semicircle is a right angle. Or take any other point, D. Join A to D, B to D, the ends of the diameter to that point on the circumference. This is 90 degrees. Then take a point here also, below the diameter, the E. What should I join? Join A to E, B to E. So now an angle is formed. An angle is formed. You can see the angle AEB. You can see the angle AEB formed on the circumference at the point E, and that angle is made by the diameter. This angle AEB is subtended, or it's made by the diameter AB at the point E on the circumference of the circle. So since it's made by the diameter, this angle is 90 degrees. So this is what is angle in a semicircle, is a right angle. All right? Okay. Chord CD, continuing with the question, CD is a chord equal to the radius of the circle. CD. CD is a chord equal to the radius of the circle. So join OC and OD, because OC, OD, radius, right? OC radius, OD also radius. So when you join OC and OD, supposing, okay, let's say, this is what we normally say, right? Radius R. So OC is R, OD is R. Then what about CD? CD is also R, because CD is a chord. Chord cannot become the radius, but its length is equal to the radius of the circle. So if the radius is R, CD is also R. If the radius is, say, 5 centimeters, CD is also 5 centimeters. What is CD? Is CD the radius? No, CD is not the radius. This is CD. CD is a line segment. And that line segment in a circle is called a chord. It's called a chord. CD is a chord because it has its endpoints on the circle. The line segment CD has its endpoints on the circle. So it's a chord. It's not the radius, but the length of CD is equal to the radius of the circle, which makes triangle COD an equilateral triangle. Which makes triangle COD an equilateral triangle, from which we understand that each interior angle is equal to 60 degrees. Each interior angle of this triangle COD is equal to 60 degrees because COD is equilateral. Because CO is already equal to DO, and now these are equal to CD also. So equilateral. Okay, so that's what we are. So from this angle in a semicircle is a right angle. Diameter angle in a semicircle is a right angle. And from this equilateral triangle, so this angle COD is equal to 60 degrees. COD is equal to 60 degrees. Now, AC and BD, when extended, intersect at a point E. AC and BD. You can see AC here. What is AC? Chord. See, AC is a line segment and it has its endpoints on the circle. So AC is a chord. When you extend the chord AC, DB or BD is also a chord. BD is also a chord. When you extend it, they meet at E outside the circle. So these two chords, AC and BD, when you produce, they meet outside the circle at E. With all this given to you, you need to show that this angle AEB is equal to 60 degrees. 60 degrees. All right. Now see here. All right. Correct. Now, angle COD is equal to 60 degrees. The same arc CD, makes angle same arc CD, no? Same arc CD makes angle, so join this. Join. So it's not a curve, it's a straight line. So I'll just tell you about the construction. Construction, you'll have to join OC, OD. You also have to join CB. CB, this one. This is 60 degrees. Now, arc CD, okay? Arc CD. Arc CD makes angle COD at the center. The same arc CD makes CBD on the circumference. CBD. See, the arc is CD. This is the arc CD. This is the arc CD. Can you see two angles? COD and CBD. COD is at the center O and CBD is at the point B on the circumference. But it's made by the same arc CD. And the theorem is the angle at the center is double the angle on the circumference. So if this is 60 degrees, this is 30 degrees. This is 30. The angle at the center is always more. That is double. On the circumference is half of the center. Angle formed on the circumference is half the measure of the angle at the center. The angle at the center is double, is twice the measure of the angle formed on the circumference. Of course, made by the same arc. It's very easy to identify the angles because you can see the arc there. CD is the arc. And you can CD is the arc. See, can you see this? CD is the arc. COD, CBD. COD is, you can see, angle at the center. CBD, angle of the circumference at B, made by the same arc. So there is a relation between these two angles. This is double, this is greater. This is double, this is half of this angle. All right. So from this, we get this angle, right? This is 30 degrees. Is that clear? Now, angle in a semicircle is a right angle. AB diameter. So this ACB is 90 degrees. ACB is 90 degrees. Because how do we identify the angle in a semicircle? AB is a diameter, C is a point of the circumference, join A to C, B to C. And angle ACB is 90 degrees. That's what we understood, right? Angle in a semicircle is a right angle. AB is a diameter. Take any point of the circumference and the point is C. Join A to C and B to C. So what's the angle formed? Angle ACB. And that's 90. Because angle in a semicircle is a right angle. Now use the exterior angle property of a triangle. So the triangle is triangle CEB. See like this. This E here, C and D. This one we found 30 degrees. And this one is 90. This is that A. Don't see this one. Don't see the other things which come in the way, you know. Focus on your triangle. Don't see all this. Just focus on your triangle. Can you see the triangle? BEC, this triangle, BEC. And the side EC is produced. You can see that flag-like triangle, right? So you can see this BEC, this triangle. That's what I've shown here, BEC, wherein you'll have to find the measure of angle E. You'll have to find the measure of angle E. Right? And we know this is 90 because the angle in a semicircle is a right angle. This one we found using center, the angle in the center 60 degrees because equilateral triangle. So this angle half of 60, 30 degrees. Both angles were made by the same arc CD. So one part is angle in a set. Okay, the most important thing is construction. Join OC, OD, and BC. That's the most important thing. Construction. Join OC, OD, BC. That's a construction. Only then you can see these triangles and you know the angles, the angle made by the diameter. Only when you join BC can you make out the angle made by the diameter because A to C is already connected. B to C you have to connect. So important. Okay, let me finish it now. So this is the exterior angle. Exterior angle is equal to the sum of the two interior opposite angles. So leave this. So 90 degrees is equal to this angle x plus 30. So x is equal to 60 degrees. All right. Let's see it quickly again. So construction, join OC, OD. AB is a diameter. We are taking the point C on the circumference. A to C is connected. B to C is not connected. So let's connect B to C. Okay. So after the construction, join OC, OD, and BC. You can say angle in a semicircle is a right angle. So this is 90 degrees. This is one part. Then you'll have to show that, or you'll have to, write out that this triangle is an equilateral triangle, and hence this angle is 60 degrees. Then you have to use a theorem which says that angle COD or angle CBD is half of COD. So this is 30 degrees. Now we are all ready. Now take the triangle. Take this triangle. This is X. This is 90 angle in a semicircle is a right angle. This is 30 because 60 by 230. Exterior angle property. X plus 30 is equal to 90. So X is equal to 60 degrees. All right. I'll share the working later. Understood? So we recalled two things. One is angle in a semicircle is a right angle. And then arc angle made by an arc at the center is double the angle made by the same arc at any point on the remaining part of the circle. And that is very easy to identify because CD, just write the name of the arc. Write the name of the arc, CD, CD. CD, CD. Oh God. CD, CD. COD is the angle made by arc CD at the center O. CBD is the angle made by the same arc CD at the point B on the circumference. So these two angles are related. Angle COD is twice angle CBD. or angle CBD is half of angle COD. Like diameter and radius. Diameter is twice radius. Radius is half of the diameter. அதே மாதிரி தான் சென்டர்ல இருக்கிற ஆங்கிள் வந்து டயமீட்டர் மாதிரி, சர்க்கம்ஃபரன்ஸ் இருக்கிற ஆங்கிள் வந்து ரேடியஸ் மாதிரி. சென்டர்ல இருக்கிற ஆங்கிள் வந்து ஆங்கிள் இந்த சென்டர்னா டயமீட்டர், ஸோ டுவைஸ் த ஆங்கிள் வந்து சர்க்கம்ஃபரன்ஸ். ஆங்கிள் வந்து சர்க்கம்ஃபரன்ஸ்னா ரேடியஸ் மாதிரி அது. ஸோ ஆங்கிள் வந்து சர்க்கம்ஃபரன்ஸ் இஸ் ஈக்குவல் டு radius, no, so twice diameter, so twice the angle at the center. Which is the greater angle? The angle at O. That's the diameter kind of. Okay. From this you can recall the theorem. Angles in the same segment of a circle are equal. Okay, angles in the same segment of a circle are equal. So what was that? Circle chord. Okay, AB is a chord because it has its endpoints on the circumference of the circle. This is the minor segment. This is the minor segment. This is the major segment. Major segment. Angles in the same segment of a circle are equal. Okay, let's understand using the major segment. Okay, so this is the major segment. This is the major segment. Take 2 points anywhere on the circumference of the major segment. Take 2 points anywhere on the circumference of the major segment. Okay, anywhere, C, D, wherever you choose, wherever you please. All right. Now join, which is the chord? AD is the chord. AD is the chord which is dividing the circle into 2 segments, right? It's because of the chord AB that we have the major segment and the minor segment, right? So AB is very important, AB. Now C and D are the points on the circumference of the major segment. Major segment. Now join A to C, B to C. Straight lines, okay? This is the angle made by the chord AB at the point C in the major segment. Now join A to D, B to D. This is the angle made by the same chord AB, but at a different point B on the circumference of the major segment. Both these angles at C and D are 2 points on the major segment, on the circumference of the major segment. So this chord AB makes angle ACB and it also makes angle ADB at the point C and D on the circumference of the major segment. ரெண்டுமே ஒரே segmentல தான் இருக்கு. இந்த ரெண்டு angles equal. Angles in the same segment of a circle are equal. Angles in the same segment of a circle are equal. Same thing holds good here. இங்க ரெண்டு point எடுக்கிறோம். இது E, இது F. You join A to E, B to E. A to F, B to F. Then this angle and this angle, they're equal because they're the angles in the minor segment. Both angle AEB and AFB are angles on the circumference of the minor segment made by the same chord AB. So they're equal. That's what is angles in the same segment of a circle are equal. Circle chord PQ, point S, point T, join P to S, Q to S, angle. Join P to T, Q to T, angle. This angle is equal to this angle. Angles in the same segment of a circle are equal. Right? So now using this, very easy to find angle BCD. DBC is 55. DBC, this one, this is 55. BAC, this one, this is BAC. BAC is 45. BAC is 45. We need to find BCD, this one. Right? So we'll take this chord. Now, if in the triangle, if you take up this triangle BCD, in the angle தெரியும் 55. In the angle கண்டுபிடிக்கணும். So you are interested in finding this angle. in triangle BCD. In this triangle, 55 தெரியும். இதுதான் கண்டுபிடிக்கணும். BCD is what we have to find. So if we can find the measure of this angle, then you can use the angle sum property. And so if you want to find this angle, no, just try to name that angle. What do you call this angle? BDC. Angle BDC. So in your mind, you're like, I want to find this angle BDC. So write another angle which rhymes with this, BDC. Is there any other angle that rhymes with this? Very good. BAC. BAC rhymes with BDC. BAC. BDC, BAC. Both these angles are made by the same chord or arc, whatever you say. Chord BC. Can you see here? BC is the chord. BC is the chord. Or you can even say BC is the arc. BC is the arc. We'll say chord because we're saying angles in the same segment are equal, no? So BC is the chord. BC makes BAD and BDC. Yes or no? BAC. Circle BC. There is A here. There is D here. BAC. BDC. This angle is 45 degrees. In the figure, this is also connected. This is connected. That's the diagram there. So angles in the same segment of the circle are equal. So this is also 45 degrees. Yes or no? BC is the chord. The points are D and C. BC is the chord. D and A are the points on the circumference. So these two angles are equal. So BAC is 45. So BDC is also 45. So you found this angle 45 degrees. So angle some property 90, 100. So this is 80 degrees. All right. You can do it in one other way. So that you should think. I don't know. So this is how you go about so you should there's a chord here. So you don't know the center of the circle here. So you cannot use angle subtended by an arc at the center is WD angle. That we cannot use because you do not know the center of the circle at all. So that's ruled out. That you cannot use. Angle in a semicircle is the right angle. Also we cannot use because we don't know that. We have two line segments like AC and BD, but they're not given to be diameters. Are they given to be diameters? No, they are not given to be diameters. So you cannot use a theorem angle in a semicircle is a right angle. So like that, when you think about the theorems, you don't have relevant information. So you're left with only this. What? Angles in the same segment of a circle are equal, for which you just need a chord. And you have to check if the chord makes two angles at two different points of the circumference. You can also use angle in a semicircle as a right angle here. Okay, let me give you that question. Use the property that in a cyclic quadrilateral opposite angle is supplementary. Use this property and find this angle. That's the other way of doing it. In a cyclic quadrilateral, opposite angles are supplementary. Yes, we know that. In a cyclic quadrilateral. Now here ABCD is a cyclic quadrilateral because the vertices A, B, C, and D lie on the circle. Okay, so it's a cyclic quadrilateral. So angle A plus angle C is 180. Angle B plus angle D is 180. 180. Use this property also. I'm not saying use only this property and find. Use this property also. Like earlier, what did we use? Angles in the same segment of a circle are equal, and then we use the angle sum property in a triangle. We use two things. What? Angles in the same segment of a circle are equal, then angle sum property. Now I want you to use something. First thing I don't know, and then find that angle using Opposite angles are supplementary in a cyclic quadrilateral. Yeah, do it. You can just roughly work in your book and just come back. Yeah.
So the theorem angles in the same segment of a circle are equal. I found angle DAC.
Yeah. So one minute. DBC. This is 55. BAC. This is 45. Yeah.
So I found angle DAC with the theorem.
D
DAC.
DAC. Yeah. Which is the other angle? Meaning DAC is equal to which one?
DAC is equal to DBC.
Yeah. So DBC, angle DBC is equal to
Angle
55 degrees. Or okay. Okay, yeah. DBC is 55 degrees. Angle DAC. Yeah, tell me is equal to
angle DBC, which is equal to
DBC. Therefore, angle DAC is also 55 degrees. Reason?
angles in the same segment of a circle are equal.
Angles in the same segment of a circle are equal. See, they're rhyming. They're rhyming, no? DAC, DBC. DBC is 55. So DAC, this is also 55. This is also 55. Yeah, next, we have to find this angle. Next.
So we already know that BAC is equal to 45. So adding the two angles, we get angle DAB.
Angle DAB is?
DAB is 100 degrees.
100 degrees.
So with the property opposite angles in a cyclic quadrilateral are supplementary, you can find angle BCD, which is 80
degrees. Therefore, DCB is equal to 80 degrees because opposite angles are supplementary. Very good. Yeah. In the first method, we found this angle. We found this one. BAC, BDC. We found this. And then we used angle sum property. BAC, BDC. See, how to make out this? You have to Name the angles given to you. How do you call this angle? BAC. Now find an angle which rhymes with that. BAC, BDC. That was the first method. We found BDC. And then we used angle sum property. Where are you seeing? Are you looking at the figure? Okay. The second method, see, in the first method, you found an angle which rhymes with BAC. BAC 45. So BDC is also 45 and then angle sum property. Second method, read this angle. Read this angle. How do you read this angle? DBC. DAC. DBC is this angle. DAC is this angle. Or you can even call it CBD, CAD. So this is 55, so this is the 55. So this angle is 100. So this is 80. Opposite angles are supplementary in a cyclic quadrant. Okay. This is simple, just go through now. I'll just come back. I'm not explaining this. So to prove that B lies on DC, see, if I have to prove that C lies on AB, see, forget this situation, like in general. If we have to prove that C lies on AB, AB is a line segment, and you have to prove that C lies on AB. So you'll have to prove that this angle is 180. That's all. If you'll have to prove that C lies on the line segment or the line AB, you'll have to show that this angle is 180 degrees. That means this one is not a broken line. It's not like CA like this and then C does not lie on C. Supposing it's like AB and C here. C does not lie on AB because this angle is 160 degrees. In this figure, C does not lie on AB. AC is a line segment, BC is a different line segment. AB is this line segment, AB is this line segment, and C does not lie on AB. So if this in this figure or this representation, since this angle is 160 degrees, C does not lie on AB. But if you can prove that this angle is 180 degrees, then definitely C lies on AB. And here we'll have to prove that B lies on DC. B lies on DC. So just prove that angle DBC is 180 degrees. Angle DBC is 180 degrees. Then yes, B lies on DC. And for that, you'll have to join construction, join AB. Construction, join AB. Sometimes the diagram will not be given. I don't know if we like for this, if I have put the diagram here by mistake because No, I'm not sure. So sometimes the diagram is not given. So you should know how to make the diagram. Like when it's not given, you have to read the question and make it. See, two circles intersect at 2 points A and B. Intersecting circles. So they will be like this. These are touching circles. These are touching circles. Intersecting circles will be like this. And one big and one small because they're not congruent circles. So two circles. So take the circles of the two circles must slightly be of different sizes. Yeah. So two circles intersect at 2 points, A and B. AD and AC are the diameters to the two circles. Prove that B lies on the line segment DC. So B lies on DC, no? So first carefully you draw that. Because நம்ம DC எல்லாம் choose பண்ணிட்டோம்னா அப்புறம் இது join பண்றது கஷ்டமாயிடும். So the first join பண்ணிடுங்க எப்படி? B lies on DC, no? So B lies on DC. So there should be D here and C here. Now AD diameter. So you should join AD. AC diameter. So join AC. So you should be able to draw the figure with the information given. If it's not given. Sometimes we know the proof, but we struggle to make the diagram or we wouldn't have practiced drawing the diagram. So even if you know the proof, are you in the proof? Make it simple. So if when you're reading, see, use NCRT for this. If the figure is not given, okay. Now for this situation, you can just try to do the figure by yourself also. The construction is join AB. And then this is 90 degrees because AD is the diameter. Angle in a semicircle is a right angle. AC diameter. Angle in a semicircle is a right angle. Look at the first circle. See this in this circle. This one is a diameter. DA, this is a diameter. B is a point on the circumference. So it is this one. 90 degrees. Those 2 points A and B, no, they lie on both the circles because the two circles intersect there. On which circle does A lie? On both the circles. On which circle does B lie? On both the circles. Because that's where the two circles intersect. The two circles intersect at A and B. Which means A is a point common to the two circles. B is also a point common to the two circles. So first circle, diameter, P is a point on the first circle. AD is the diameter. Join D to B, A to B. That's why construction join AB. That's why construction join AB. This is 90 degrees. Angle of semicircle is a right angle. Second one, second circle. Second circle. And where is this point B on the second circle? Yes, it is on the second circle. And then AC is the diameter. It's given, AC is the diameter is given. Join the ends of the diameter to this point to B. Join C to B, A to B. 90 degrees. Angle of semicircle is the right angle. So now the sum of these two angles is 180, which means this angle DBC is equal to 180 degrees, which proves that B lies on DC. All right. Prove that the quadrilateral formed by the internal angle bisectors of any quadrilateral is cyclic. Prove that the quadrilateral formed by the internal angle bisectors. These are the internal angles or the interior angles. These are the interior angles. Bisectors. Okay, bisectors. All right. So you need to prove that this is the quadrilateral. This is the quadrilateral made by the bisectors of the interior angles or the internal angles of this quadrilateral. You need to prove that this is cyclic. This quadrilateral is cyclic. A, B, C, D. So these are the bisectors, right? So how much is this? This one is half of angle A. And what about this? Half of angle. This half of angle A, this half of angle B, this half of angle C, this half of angle D, because they're the bisectors. Since we've in my situation once or twice பார்த்திருக்கோம் முன்னாடி so நான் ரொம்ப டீடைலா சொல்லல figure. We understand bisectors, they meet and we proved it forms a rectangle earlier, right? In a parallelogram. In quadrilaterals, we proved that. Prove that the bisectors of the interior angles of a parallelogram is a rectangle. Okay. What about this half of angle B? And what about this half of angle C, half of angle D? Now let's name this quadrilateral P, Q, R, S. Now we are going to prove that angle P plus angle R is equal to 180. So it's cyclic. You can also prove that angle Q plus angle S is 180. So it is cyclic. Any one pair of opposite angles. No, அதுதான் தண்ணி working. I'll take off my phone. Okay. We'll have to prove that PQRS is cyclic. So we are going to prove that angle P plus angle R is equal to 180. Very, very simple. In triangle PAB. Okay. In triangle PAB. We're going to find the expression for angle P. We're going to find the expression for angle P because we're going to find the expression for angle P. We're going to find the expression for angle R. Then we're going to add both the expressions, angle P plus angle R. And when you add the two expressions of angle P and angle R, you will get 360. Sorry, 180. Therefore, it's cyclic. So in triangle PAB, angle sum property, half of angle A plus half of angle B plus angle P plus angle P. Okay, angle P is what? Okay, just to understand, I'll mark it 1, okay? Plus angle 1 is equal to 180, correct? In triangle PAB, this is only half of A, this is half of B. Plus angle 1 is equal to 180. So what is angle 1? Angle 1 is equal to 180 degrees minus half of angle A minus half of angle B. All right. So we got the expression for angle 1, which is P. In triangle CDR, what did I say? PAB. No, so let me say RCD. RCD. In triangle RCD, half of angle C plus half of angle D plus angle 2 is equal to 180. Angle sum property. When we see the triangle RCD, where the three interior angles are 2, half of C and half of 2. So from this, the expression for 2 is angle 2 is equal to 180 minus half of angle C minus half of angle B. So we got the two expressions. We got the expressions for angle 1 and angle 2. Now let's add. Angle 1 plus angle 2 is equal to 180, 180, 360. Minus half angle A, minus half angle B, minus half angle C, minus half angle D. Okay, so this is equal to 360. Take out minus half common. So in bracket, angle A plus, because minus into plus is minus, angle B plus angle C plus angle D. Correct? Minus into plus is minus. So now in quadrilateral ABCD, what is the sum of all these four angles? 360. Because angle A means the whole of angle A. Angle A is the whole of angle, because when we said half of angle A, it is this whole A, right? Yeah, so half into 360 degrees. 180. So you get 360 minus 180, which is 180 degrees. So what do we prove? Angle 1 plus angle 2 is equal to 180, which means angle P plus angle R is 180. One pair of opposite angles
Are
supplementary. Therefore,
PQRS is a cyclic quadrant.
PQRS is a cyclic quadrant. All right, that's it. Next one. All right, next one. We'll just keep the numericals aside. I'll finish the proof of this exercise. We'll come to the numericals later. A chord of a circle is equal to the radius of the circle. We saw a similar situation in the example. Chord CD is equal to the radius. But small chord CD equal to the radius. So equilateral triangle. Yeah. So here also chord C, sorry, a chord of a circle is equal to the radius of the circle. So you don't have to take a tiny one. You can take one like this here. A chord of the circle. So you can take this chord AB, whose length is equal to the radius of the circle. So center O. This is equal to R. So this is R radius. So this one is an equilateral triangle. So this is 60 degrees. If you want, you can use the 60. If needed, whichever is needed, we can use. Whichever is useful, we can use later. Okay. AB is a chord whose length is equal to the radius of the circle. That makes triangle AOB an equilateral triangle. Find the angle subtended by the chord at a point on the minor arc and also at a point on the major arc. Now by our diagram, this is the minor arc. This is the minor arc. And this is the major arc. Major arc. Okay. Okay, just ignore this one, okay? Just take this. Major arc, correct? Now you're supposed to take a point. Let me read that again for you. Find the angle subtended, meaning made by the chord AB at a point on the minor arc. At a point on the minor arc. And also at a point on the major arc. Just to understand, we'll take it in the middle like this. Circle with center O. AB is a chord whose length is equal to the radius of the circle. Triangle AOB is equilateral. C is a point on the minor arc. D is a point on the major arc. So we need to find the measures of these angles. The angles subtended by the chord at a point on the minor arc and at a point on the major arc. So you need to find, see, this is the chord. So join A to C, B to C. You need to find the measure of this angle. Join A to D, B to D. You need to find the measure of this angle. Find the angle subtended by the chord AB at a point on the minor arc C and also at a point on the major arc D. Find those angles. This 60. This is like diameter angle, no? So this is 30. Because angle at the center, AOB, ADB. AOB, ADB. So if AOB is 60, ADB is 30. Now identify the cyclic quadrilateral here. Identify ACBD. ACBD is a cyclic quadrilateral. ACBD is a cyclic quadrilateral. Opposite angle supplementary. This is ACBD. How much is this? 30. Then how much what will be the measure of this angle? 150. So the angle on the minor arc is 150 degrees. The angle on the major arc is 30 degrees. The angle on the minor arc is 150, major arc is 30. Okay? Okay. If the diagonals of a cyclic quadrilateral, so the given figure is a cyclic quadrilateral. If the diagonals of a cyclic quadrilateral are diameters of the circle, okay, let me draw. Now, what is the end thing we'll have to prove? Prove that it's a rectangle. So we need to draw the figure like a rectangle. A, B, C, D. So A, B, C, D is a cyclic quadrilateral. Yeah, okay. And the diagonals of the quadrilateral. Okay, the diagonals of the quadrilateral. AC diagonal, BD diagonal. The diagonals are the diameters of the circle. What are AC and BD for the quadrilateral diagonals? The same line segments are diameters for the circle. See, there are two people here. There are two things here, quadrilateral, circle. And there are two line segments, AC, BD. These two line segments have different relations with the two things, quadrilateral and circle. The two line segments, AC and BD. How are they related to the quadrilateral? They're the diagonals. To the quadrilateral, they're diagonals. They're also related to the circle. How? They're diameters of the circle. So which means this is the center of the circle. This is the center of the circle. It's not given. It's not mentioned anywhere. But you know the diameters intersect at O. In every circle, the diameters, when you take two diameters, they will intersect at O. See, even if you take diameters like this, O. Okay. If the diagonals of a cyclic quadrilateral are diameters of the circle through the vertices of the quadrilateral, okay, that we understand. Okay. Prove that it's a rectangle. That's why we already drew the quadrilateral ABCD to look like a rectangle. That's what you'll have to prove. What's the definition of a rectangle?
It is a parallelogram.
Correct. A parallelogram in which one angle is a right angle. Yeah, a parallelogram in which one angle is a right angle is a rectangle. A rectangle is a parallelogram in which one angle is a right angle. So we need to first prove that ABCD is a parallelogram and then prove one angle of this parallelogram is 90 and hence it's a rectangle. Okay. But what is it now? It is only a quadrilateral. It's a cyclic quadrilateral. What is ABCD now? It is a quadrilateral. It's a cyclic quadrilateral. So from there, you'll have to promote it to a parallelogram and further promote it to a rectangle. So how is a quadrilateral, or how can a quadrilateral be promoted to a parallelogram? There are so many criteria, right? So here when both the pairs of opposite sides are parallel, it's a parallelogram. When both pairs of opposite sides are equal, it's a parallelogram. Opposite angles are equal. When both pairs of opposite angles are equal, it's a parallelogram. What we're going to use here is when the diagonals bisect each other, it is a parallelogram. In a quadrilateral, when the diagonals bisect each other, it's a parallelogram. That is, if the diagonals have the same midpoint. Diagonals bisect each other, meaning if the diagonals have the same midpoint. What is meant by diagonals bisect each other? Both the diagonals will have the same midpoint. So here, which is the midpoint of the diagonal AC? Let me ask you slowly. Diagonal AC. ABCD is a quadrilateral, right? What is AC? Diagonal. Which is the midpoint of the diagonal AC? O. Because we know that's the center and because that's a diameter also. That's a diameter also. So O is the midpoint. Now BD diagonal, which is the midpoint? O. Because BD is also diameter and O is the midpoint. So if both the diagonals have the same midpoint, then the diagonals bisect each other. So in quadrilateral ABCD, the diagonals AC and BD, they have the same midpoint, which is O. They bisect each other. And hence ABCD is a parallelogram. How do we know that O is the midpoint of AC and BD? That is because that's not by them being diagonals. That is by these line segments being the diameters for the circle. That's how we know that O is the midpoint. O is the midpoint not because they're diagonals, but because they're diameters of the circle. AC is the diameter of the circle. O is the midpoint. BD diameter of the circle. O is the midpoint. They're also diagonals. So you just have to say that the diagonals of ABCD, they bisect each other, and hence ABCD is a parallelogram. Now, take one diameter at a time. Okay, AC is, so like, நமக்கு வேணா diagonal பார்ப்போம் வேணும்னா diameter பார்ப்போம். That is according to we are very, like, as in how we like, we want, to our favor. So like to prove it's a parallelogram, we treated AC and BD as diagonals. To prove ABCD is a parallelogram, we took AC and BD as the diagonals having the same midpoint O, and so it's a parallelogram. Now to show 90 degrees, no, we'll take AC as the diameter of the circle. We'll use that. Now AC is the diameter of the circle. So D is the point of the circumference. Join A to D, C to D. This is 90 degrees. Angle in a semicircle is a right angle. Where you have diameter, you can use this theorem. Angle in a semicircle is a right angle. Where you have diameter, you can use this theorem. Angle in a semicircle is a right angle. AC diameter, angle D 90 degrees or angle B 90 degrees. If you take BD as the diameter, BD as the diameter, angle BCD is 90 degrees, angle BAD is 90 degrees. BCD, BD diameter, BCD, BAD, 90 degrees. Here AC diameter, ADC, ABC, 90 degrees. You can mention any one of these four. You don't have to write all the four. You just have to mention any one of these four. So in the parallelogram, one angle is 90 degrees, therefore it's a rectangle. All right. What we understood is AC and BD are dash of ABCD. AC and BD are dash of ABCD. Diagonals of ABCD. AC and BD are dash of the circle. Diameters of the circle. If AC and BD are diameters, where will they intersect? At the center. At the center of the circle, which is O. Because they're diameters, they have to meet at O. Which means O is the midpoint of AC. O is also the midpoint of BD. So the diagonals. We got midpoints using diameters. Now to prove it's a parallelogram, you must say diagonals. The diagonals have the same midpoint. Not the diameters have the same midpoint. Because you're proving that the quadrilateral is a parallelogram. You're proving that the quadrilateral is a parallelogram. So don't say that they're diameters. We get that. We understand that O is the midpoint of AC and BD because they are diameters. But now that's over. We got that information from there. Now AC and BD are the diagonals of the quadrilateral ABCD and O is the midpoint of both the diagonals. So they bisect each other. Hence, it's a parallelogram. One angle is 90 degrees because we have two diameters. So that you understand. So you can prove any one of the four angles to be 90 and hence it's a rectangle. Just a minute. All right. If the non-parallel sides of a trapezium are equal, if the non-parallel sides of a trapezium are equal, okay. So what do you call a trapezium in which the non-parallel sides are equal? Isosceles trapezium. An isosceles trapezium is one in which the non-parallel sides are equal. Yeah. Okay, let's call it ABCD. ABCD is an isosceles trapezium. Okay. In trapezium ABCD, the non-parallel sides are equal. So this side is equal to this side. These two are the parallel sides. Prove that it is cyclic. That means an isosceles trapezium is always cyclic. If the non-parallel sides of trapezium, so they're talking about an isosceles trapezium, prove that it's cyclic. So an isosceles trapezium is always cyclic. A trapezium need not always be cyclic. Okay. An isosceles trapezium is always cyclic. Okay. Like a square and a rectangle. A rectangle, you can always draw a circle passing through the four vertices of a square or a rectangle. Both square and rectangle are cyclic quadrilaterals because you can see their opposite angles are supplementary. 90, 90, 180, no? In a square and rectangle, opposite angles are supplementary. So they are cyclic. In the same way, here the angles are not 90 each, but the opposite angles are supplementary. That's why it's cyclic. In square and rectangle, opposite angles are 90 each. 90, 90, 180. But here the angles are not 90 each, but maybe like this is 130 and this is 50, and so it's cyclic. Okay, but here you cannot find the measure. You'll have to prove that A plus C, angle A plus angle C is 180. You can also prove that, or you can prove that angle B plus angle D is 180 to prove it's cyclic. So this proof you've seen earlier, meaning, okay, the question reads different in the chapter quadrilaterals. There you have to prove some two triangles are congruent and then angle, prove that D is equal to C, A is equal to B, and then diagonal AC is equal to diagonal BD. In quadrilaterals, the last proof. Okay, so you know most of this proof which I'm going to tell you now, most of this proof you know, only the last part will be new to you. So construction, draw AM perpendicular to CD and BN perpendicular to CD, construction. Now you'll have to show that these two triangles are congruent to each other. Angle 1 is equal to angle 2, 90 degrees by construction. AD is equal to BC given hypotenuse. AM is equal to BN because the distance between two parallel lines is the same everywhere. AM is equal to BN. Angle 1 is equal to angle 2, 90 degrees by construction. AD is equal to BC given, and AM is equal to BN because the perpendicular distance between two parallel lines is the same everywhere. So this makes RHS congruence criterion. The two triangles are congruent. CPCT, this angle is equal to this angle. இது வரைக்கும் உங்களுக்கு தெரியும். இது வரைக்கும் தெரியும். Now just two more lines and you'll understand this proof. Is angle A, okay, we proved that angle 3 is equal to angle 4. Okay, CPCT and angle 3 is equal to angle 4. CPCT angle 3 is equal to angle 4. Okay, okay. Let me call this 1. You can use angle 1 or you can use angle 2. Any one you can use. Any one you can use. Now 3 is equal to 4 CPCT. We are there now. Okay. Now, is angle 1 plus angle 3 180? Is 1 plus 3 180? Is angle 1 plus angle 3 180?
Yes.
Why?
Co-interior angles.
Co-interior angles are supplementary. Parallel lines. Opposite sides are parallel. No, AB is parallel to CD because it's a trapezium. Allied angles are always found in the C formation. Allied angles are found in the C formation. Corresponding angles in F formation. And alternate angles in Z formation. In Z, like you rotate Z, so not a perfect Z always, it may be like this or it may be like this. So Z or Z rotated, you find the pair of alternate angles there. And F may look like this also, sometimes an angry F, like it's looking down like this also. So that F here and here are corresponding angles. Or it can be like this also, so like parallel lines, transversal. This angle is equal to this angle, corresponding angles. So corresponding angles always in F. Z, alternate angles. C, corresponding angles. Corresponding C, you can remember. Corresponding, so C. So you can see the C here. So in this formation, two lines must be parallel. And the other one should be the transversal. So see here, parallel line, transversal, parallel line. This angle and this angle. They are allied angles. Co-interior angles. They are supplementary. Okay, they are supplementary. So angle 1 plus 3 is equal to 180 is correct. Co-interior angles are supplementary. Now what you want to prove? What is it you want to prove? Angle 1 plus. What is it we want to prove? We are interested in proving that angle 1 plus 4 is 180. Keep that in mind, okay? What is that you want? Angle 1 plus 4 is 180. You want to prove this. You want to prove 1 plus 4 is 180. But 1 plus 3 is 180. Now, how do you convert this to 1 plus 4? You got it. 1 plus 3, 180. How do you convert this to 1 plus 4 is 180? It's right in front of you. What is the opposite? What makes it so difficult? I don't know. Congruency we understood? Okay. Angle 3 is equal to angle 4, CPCT.
Since angle 3 is equal to angle 4.
Yeah. That's all. Angle 3 is equal to angle 4, CPCT. Okay, so angle 1 plus 3 is 180 allied angles. Now replace 3 with 4. Angle 1 plus angle 4 is equal to 180. That's why we prove 3 is equal to 4. So 1 plus 4 is 180. Opposite angle is supplementary. So it's cyclic. You can also see, you should like decide on what you want to prove. Suppose you want to prove that 2 plus 3 is 180. You want to prove that 2 plus 3 is 180. You must write that in a corner. What is it you want to prove? Okay, you want to prove that 2 plus 3 is 180. So your goal should be fixed. This is your goal. I want to get 2 plus 3 is equal to 180. So I should write, sorry, நான் நிறைய இடத்துல 2 போட்டிருக்கேனோ? Sorry. I don't know if I confused you. Sorry. I don't know if I should have marked this 5 and 6. There was already 1 and 2 here. Did that confuse you?
Yes.
So sorry, I didn't notice that. I should have numbered it 5 and 6. Okay. I don't think I have to clarify that. You can get it now, right? Okay. Okay, let's fix both. Like we'll do this and the other one again. 1, 2, 3, 4, 5, 6. Yeah. Now, okay, so we need to prove, so then it's not going to be 2 plus 3. Because at mark 1 and 2 in two different places, it might have been confusing. I didn't realize it. Okay. Let me start from here. So our intention is to prove that angle 5 plus angle 4 is 180. Okay. Correct? 5 plus 4 is 180. Am I right? Opposite angle is supplementary. So it's cyclic. Okay. We know 5 plus 3 is 5 plus 4 we want, but we know 5 plus 3 is 180. Why? Allied angles or co-interior angles. Now 5, but you want 5 plus 4. 3 is equal to 4. So replace 3 with 4. 5 plus 4 is 180. Cyclic quadrilateral. If you want to prove that 6 plus 3 is 180, angle 6 plus angle 3 is 180. If you want to prove 6 plus 3 is 180. You know 6 plus 4 is 180. 6 plus 3, 180 you want to prove, but you know that 6 plus 4 is 180 for the same reason. Allied angles are supplementary. 6 plus 4 is equal to 180. But 3 is equal to 4. So this 4 is 3. So 6 plus 3 is 180. Opposite angle is supplementary. So it's a cyclic quadrilateral. It's a very simple proof. You just have to take up this construction, show that these two triangles are congruent. CPCT 3 is equal to 4. That's all. And then all this. I'll just write this one. Try to help yourself. Read the question, go through have a look at the diagram, and you should give me the reasons. Okay. Don't tell me now. Tell me later. Meaning, tell me when I request you to say. AC. This is true. What I've written is true. I want you to say the reason. I want you to say the reason. Just put an empty bracket like that. So this is the proof. Okay, you have to tell me the reasons. I'll just come back, think about it. Yeah. Yeah. Reason?
For angle 1 and 3 angles of the same segment.
Correct.
Miss, for angle 2 and 4 angles of the same segment.
Of a circle are equal. Correct.
For 1 and 2, I think it's vertically opposite angles.
Correct. Vertically opposite angles. Correct. Correct. 1 is equal to 2 because vertically opposite angles are equal. See here. PQ is a line segment. PQ is a line segment. And AD is another line segment which intersect at B. So vertically opposite angles are equal. So 1 is equal to 2, vertically opposite angles are equal. Vertically opposite angles. Angle 1 is equal to angle 3. Name angle 1 PBA. PBA. This one is PBA. Name angle 3 PCA. Rhyming. PCA. PBA. PCA. So they are made by the same arc. PA. They are made by the same arc PA at the points B and C. B and C are the points where the two circles intersect. So B and C are points on both the circles. B and C are the points where the two circles intersect. These two are, you can see two intersecting circles there. So B and C are points that lie on both the circles. PBA. PBA. PA is the arc, B is the point of the circumference. PBA, correct. And then PCA. Angles in the same segment of a circle. Angles in the same segment. In the same segment, that's the reason. Angle 2 is equal to angle 4? Yeah, how do you name angle 2? Angle DBQ. 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 And angle 4?
DCQ.
DCQ. DCQ. DBQ. DCQ. Made by the same arc DQ. At the points B and C. DBQ is B, DCQ is C, B and C. B and C lie on both the circles. Angles in the same segment. In the same segment are equal. So from these three results, 1 is equal to 2, but 1 is equal to 3 and 2 is equal to 4. 1 and 2 are equal, but 1 is equal to somebody else 3 and 2 is equal to somebody else 4. But 1 and 2 are equal, so 3 and 4 are also equal, right? To understand, you can just use some letter like x. 1 is equal to 2. So like say, we'll say x, x. 1 is equal to 2, x, x. Now there's 1 here, no? So there's x here. So that means this is also x because 1 and 3 are equal. There's 2 here. And what is 2? 2 is x. 2 and 4 are equal. So this is also x. So we see x everywhere. X, 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 x. So 3 is equal to 4. You can see 3 is x, 4 is also x. So 3 is equal to 4. From 3 is equal to 4 result follows from the results 1, 2 and 3. From 1, 2 and 3, angle 3 is equal to angle 4. And that's what we have to prove. ACP is equal to QCP. All right? Okay. This is, can you recall this one?
Yes.
Yeah, so we just saw this in the example. Adhe proof tha. Adhe proof tha, so you can help yourself. இதோட proofs முடிஞ்சிரும். அதனால I'll do the 12th one. I'll do this one and then do the 11th one. With this, all the proofs of circles are done from your NCRT textbook. I think we have time for numericals also. Okay. All right. Prove that a cyclic parallelogram. So cyclic, okay, Parallelogram. Prove that a cyclic parallelogram, so it's a cyclic quadrilateral and also a parallelogram, is a rectangle. Is a rectangle. So if you draw the figure, look like a rectangle, ABCD. Now, this one is already a parallelogram. So to prove it's a rectangle, just one thing you have to do. One angle is 90 degrees because it's a cyclic parallelogram. It's not a cyclic quadrilateral. It's a cyclic parallelogram. It's already a parallelogram. So you just have to show that one angle is a right angle. So it's a rectangle. Okay. Now, correct. Where are we? Sorry, where is it in the question? Parallelogram. So just one step to go. Angle?
A is equal to angle C.
Very good. Angle A is equal to angle C. What's the reason? Because it's a parallelogram, opposite angles are equal. Very good. Yes.
And A plus C is equal to 180 degree because it's a cyclic
Quadrilateral. Correct. Because it is cyclic, A plus C is 180. Very good, Sanjay. Because it is cyclic, A plus C is 180. But because it's a parallelogram, A is equal to C. A plus C is 180. A is equal to C. So you can take out this and make it A. So twice of angle A is equal to 180. Angle A is equal to 90. Angle A is 90. So it's a rectangle. You can even write angle B is equal to angle D. Why is angle B equal to angle D?
What is
In a parallelogram, yeah, in a parallelogram, opposite angles are equal. It's a cyclic parallelogram. So it is cyclic and it's also a parallelogram. So from the parallelogram being cyclic, we get this result. A plus C is 180. Or you can even write angle B plus D is 180. Anyone? Correct? Anything. But angle A is equal to angle C because it's a parallelogram. Or you can say, but angle B is equal to angle D because it's a parallelogram. So on replacing, you can even take out A and make it C. Or you can take out C and make it A. Here, any one you can write, not both. Here, instead of B, you can use D. Or instead of D, you can use B. Whatever. So if you take out this and put it as C, twice of angle C is 180. Angle C is 180 by 290. So you can prove A, B, C, D, anything has 90 degrees, depending on what you replace. Correct? ABC and ADC are two right triangles. ABC and ADC are two right triangles with a common hypotenuse AC. Okay. Prove that angle CAD is equal to CBD. Okay. I think if I show this one, it might be confusing. ABC, ABC. So see here. Sorry. So these are two right triangles with a common hypotenuse. So two right triangles with a common hypotenuse. So the triangles can be on the same side of the hypotenuse or on the opposite sides of the hypotenuse. So we have two cases. Case one, here. AC is the hypotenuse. ABC, ADC. ABC, ADC. ABC, ADC, correct? We need to internalize what is given. What is given? Two right triangles. And they have A common they have their hypotenuse is common. Okay, two right triangles, common hypotenuse. Which is the hypotenuse? AC. So you can see here, AC. The triangles are ABC, ABC. Both of them lie on the same side of the hypotenuse. But the situation can be this also, right? AC, the common hypotenuse, ABC like this, and ADC like this. Now, don't say the other thing is the two triangles lie below. That is the same situation, right? The two situations are case one. Case one, the two right triangles lie on the same side of the hypotenuse. Same side can be above or below. That is the same situation. They can lie above or below. They're not two different things. You have it out there?
How can that be? We cannot have CBDs done.
We have to join. If you can't see the angle, then you'll have to join. Okay. So the common hypotenuse is AC. The two cases are the two triangles lying on the same side of the hypotenuse, opposite side of the hypotenuse. This is same side. Same side. Okay, this is the triangles lying on the opposite sides of the hypotenuse AC. Is that clear? You need to prove that CAD, which is CAD, CAD, this one, this angle CAD is equal to CBD. CBD. So you'll have to join CBD, this one, CBD. Okay. Okay. Now, since ABC and ADC, both these angles are equal to 90 degrees, that means if you draw a circle, it will pass through the points A, B, D, and C. See, it will pass. Why? Why? Because we have angle in a semicircle is a right angle, right? Here, AC is the common hypotenuse, which will be the diameter. B, D. Can we draw a circle? Can we draw a circle passing through the points A, B, D, and C? The answer is yes. Because now if you draw a circle, that information still holds true because AC can be the diameter, making ABC 90 degrees angle in a semicircle right angle, also making ADC 90 degrees angle in a semicircle is a right angle. Does anything go weird when you draw a circle? Oh, how is it possible when you draw a circle, this information doesn't, look appropriate? No. When you draw a circle passing through these 4 points, A, C, D, and B, all those things still, fit well here. You can treat AC as the diameter. So ABC is 90 and ADC is 90. Angle in a semicircle is a right angle. Correct? So there is, and there's also a theorem which has been removed from your syllabus. Yeah, it's actually based on that theorem. Okay. So since it's not a part of your syllabus, I'm not mentioning it. So this is what it is. Where did I stop? Yeah. Now, what is it? You'll have to prove that CAD. Where is CAD? This one is equal to CBD. They're rhyming, no? CAD, CBD. CAD. CD is the arc. CAD, CBD. Angles in the same segment of a circle are equal. So they are equal. Angles in the same segment of a circle are equal, so they're equal. CAD, CBD, correct? Okay. Yeah, we can't make out CBD. You will have to join BD. CBD angle இல்ல நீங்க join பண்ணாதான் தெரியும் இந்த angle. BD join பண்ணாதான் இந்த angle தெரியும். Okay. This is the first case or one case where they lie on the same side of the hypotenuse. இங்க வந்து angle B plus angle D is 180, right? Can you just turn it on for some time? Now, ABCD is a cyclic quadrilateral because opposite angle is supplementary, 90, 90, 180. So there is a circle passing through all these 4 points. Because it's cyclic quadrilateral. Now, CAD, where is CAD? This is CAD. Where is CBD? CBD, CBD. You have to join this. CBD is here. CBD is here. CAD is here. CBD is here. You have to join. And why are they equal? For the same reason. Angles in the same segment of a circle are equal. அதே reason தான். ரெண்டு கேசஸ்க்கும் reason அதுதான். Why are they equal? Because angles in the same segment of a circle are equal. இந்த theorem use பண்ணோம்னா, to use this theorem, angles in the same segment of a circle are equal, ஒரு circle வேணுமே. Circle சும்மா வரைய முடியாது. You should prove that you can draw a circle passing through those 4 points, right? To prove, okay, CAD is equal to CBD because angles in the same segment of a circle are equal. But for that, you need a circle. So in the first case, you can draw a circle. Because that information does not change. அப்படியே அந்த figure ஒரு circle குள்ள போட்டாக்க AC becomes the diameter. And then ABC, this angle. And this angle is equal to 90 degrees, still look good because angle in a semicircle is a right angle. So you can draw a circle passing to these 4 points. And then you should say that this angle is equal to this angle because angles in the same segment of a circle are equal. In the next case, you can again draw a circle passing to the 4 points because it's a cyclic quadrilateral. Opposite angle is supplementary. So they're equal. The two angles are equal for the same reason. Angles in the same segment of a circle are equal. Okay. If you're curious to know about the theorem, what is the theorem which is deleted from our syllabus? I'll tell you. Listen carefully. If a line segment joining 2 points, okay. So according to this one, I'm explaining with respect to this figure. This is the theorem. Okay. What I'm saying now is a theorem. I'll use the letters or the vertices used in this figure. If a line segment joining 2 points, subtends equal angles at 2 other points lying on the same side of it. So this line segment should subtend equal angles at 2 other points lying on the same side of it. B and D are the 2 other points lying on the same side of AC. And AC subtends equal angles. Equal angles. Yeah, because ABC is 90 degrees. And ABC is also 90 degrees. So if a line segment joining 2 points subtends equal angles at 2 other points lying on the same side of it, then the 4 points are said to be concyclic. That's a theorem. That's why we are able to draw a circle passing through these 4 points. The class is still 9:50. Okay. If a line segment, Sanjay is like, okay. No, I already texted at 7:15. I posted in the group that the class is till 9:50. Your parents are aware. If a line segment joining, because I started at 7:15, so if a line segment joining 2 points subtends equal angles at 2 other points lying on the same side of it, then the 4 points are said to be concyclic. It's a theorem. Okay. So I'll also mention this theorem when I share the answers. Okay. You can use it. Not that you should not use, but I'm not sure because just check with your classwork how your teacher has, worked this. Okay. So that's about this one. So with this, we have completed all the proofs from this chapter, circles. Okay. All right. We'll just do this one and wind up the session for today. Tell me, what's the measure of angle ADC? How much is ADC? AO? Okay. What is this angle? ABC. How can it be half of AOB? Are they rhyming? ADC and AOB, are they rhyming for you? Then ADC? AOC. ADC, AOC. So how much is AOC? 90. Then how much is ADC?
45.
45 degrees. 45, because center is only powerful. This angle is very powerful. That's only more. This one is half of it. So AOC. AOC, this one is 90. So this one is 45. So you should write, how do you write it? You just have to write angle ADC is equal to half of angle AOC. So half of 60 plus 30, 90. So 45 degrees. So 45 degrees. Reason? Angle subtended by an arc at the center. Which is the arc here? AC is the arc. This is the arc. AC is the arc. Angle subtended by an arc at the center is double the angle subtended by the same arc at any point on the remaining part of the circle. All right, children. So that's it for today's session. Online children, you can leave the call. Thank you. Good night. Thank you, children.
Thank you, ma'am.
Thank you.